Hi everyone. So in this video, we're going to talk about confidence intervals for proportions. So looking back with sampling distributions for proportions, we knew the population proportion. I have another video where I use an applet to show how the sample proportions bounce around the population proportion. Please check it out because it's definitely one of the best applets I've seen for this. So what we see in that is that the sample proportions kind of bounce around the population proportion, right? We get some up here and some down here. Sometimes it hits the population proportion, sometimes it's way off. And we know that when we have a higher sample size, the bouncing does a little less. It kind of stays closer to P, whereas if we have a smaller sample size, it can be way out here. But we know that distribution is normal, and we know the mean and the standard deviation for that distribution, which means that we have the empirical rule. Remember from chapter 5, the empirical rule that 68% of the data is within one standard deviation, 95% is within two standard deviations, and 99.7% is within three standard deviations. So we're going to use that idea when we're talking about confidence intervals. So confidence intervals goes in the other direction. Now we don't know the answer, right? In what we're doing with a confidence interval is we took one sample. We have one p hat, and we want to make some kind of inference about p. But we don't know which p hat that we have. Do we have one that's really close to p? Is it above p? Is it below p? Is it really far from the true proportion? We have no idea. All we know is that we have this sample p hat. But when we talk about distance, it doesn't really matter the perspective. So for example, if I say that I live 2 miles from the gas station, that's the same as saying that the gas station is 2 miles from me, right? It doesn't matter really the order in which I say that, meaning it doesn't really matter who's at the center of the discussion. So over here, the center of the discussion is the true proportion. We know what it is. Over here, the center of our discussion has to be this sample proportion because it's the only thing that we have. And if we know that over here, 95% of these sample proportions are within two standard deviations of the true proportion, then we know that the probability that this sample proportion is within two standard deviations of the population proportion is going to be 95%. So that's basically, there you go, there's confidence intervals. No, I'm just kidding. So I know that's confusing to hear at first. So, but I'm going to keep kind of building on this idea. So again, keep in mind that we know that 95% of p hats are within approximately two standard deviations of the population proportion, which means that we know that this p hat has a probability of 0.95 of being within two standard deviations of the population proportion. So we want to be able to talk about this in terms of standard deviations. The problem is that when we did a standard deviation for the confidence intervals, we had square root of pq over n. But now I don't know what p is, right? I don't know the population proportion. I only know the sample proportion. So I also don't know the standard deviation. So all this talk about being within two standard deviations doesn't really matter if I can't know the standard deviation, right? So what we do is we use the next best thing, the only thing that we have, which is the p hat, the sample proportion. It's the only thing we have is this one little sample. And instead of calling it a standard deviation, we now call it a standard error. And so it's the same formula, we're just using the sample proportion instead of the population proportion. And so then what we say is that we know that there's a 95% chance that P is within approximately 2 standard errors of the P hat that we have. Again, we're kind of building off the pattern that we had before and just using the only thing that we really have, this P hat. So that 95% chance, that came off of, the number of standard errors came off the fact that we were saying there was a 95% chance, right? If I had said 68% chance, we would have said then it's within approximately 1 standard error of P. This idea, this 95% chance or the 68% chance, it's called the confidence level. Or the C level you'll see in your calculator. And so the number of standard errors is based on this confidence level. When we change the confidence level, we change the number of standard errors, that is the distance between the P hat and the P. So this piece right here is really important. Remember that when we talked about the number of standard deviations that something was, we called it a z-score. So we calculated a z-score, and if we got something like 1.5, we said that that data value was 1.5 standard deviations above the mean. Well, now we want to talk about the number of standard errors that something is from that P hat value. And instead of calling it a z-score, we call it a critical value. And we use the notation Z star. It's always going to be a positive value. And just like we did before when we needed to find a value based on a percent, we're going to use the inverse norm command. So if we want to know what Z star is for a confidence level of 95%, that's a central 95%. So we would use the inverse norm command with 0.95. In this case, we're talking about z-scores. So remember that the mean z-score is 0 and the standard deviation is 1. So we use a 0 and a 1. And then for the newest model, you choose center here and you get 1.96. For the older models, you have to use the left area, which means that you have to break up the remaining 5%, which remember that the normal model is completely symmetric. So we'd have 2.5% above that central 95% and 2.5% below. And so when we add the central 95 plus that lower 2.5%, we get this 0.95. And then you'll get the same critical value here. We did problems like this in chapter 5. But I have a little table here of the most common critical values. And so this is Z star. So you can write these down, put them somewhere, have them handy for the test. The ones that are most important to us are these right here. So we're going to talk about confidence levels of either 90%, 95, 98, or 99. Those are basically the only ones that you're going to see. So if you write down this little table, you don't really ever have to go using your inverse norm command to find Z star. Okay, so what is a confidence interval? What's the formula for it? So we have P hat at the center of our interval. So we have some interval, P hat is at the center, and we're trying to capture the population proportion. And we're saying that if we add a certain number of standard errors this way and a certain number of standard errors this way, we're going to get this interval, and we're going to say that we are 95% confident or 90% confident that the population proportion is within this range of values. So when we look at this formula here, remember Z star is the number of standard errors, and this square root of P hat Q hat over N, this is the standard error. When we multiply that by a Z star, this is called the margin of error. And you've probably heard that term before because whenever they talk about samples in the news or anything like that, you hear about the margin of error. Well, hopefully you hear about the margin of error. The confidence intervals, when calculating these, they have the exact same assumptions and conditions as the sampling distribution for proportions. All right, so I'm going to do a quick example of finding a confidence interval for proportions by hand, but I do not ever want you to do this. We're going to use your calculator to find confidence intervals, and I'll show you that on the next slide. It's not hard. I'm not saying that it's hard, but we're going to learn 5 of these, and they are going to get more complicated. The point of these is not the physical calculation of these confidence intervals. The point of the confidence intervals is to be able to interpret them and know what they're saying. That is far more important than the physical calculations, which is why we're just going to use our calculator to let that do the grunt work and us do the more important interpretation of what we're finding. But I want you to see it by hand just so that you kind of understand what your calculator is doing behind the scenes. So a quick, here's our example. It says the National Association of Music Merchants surveyed 500 parents of children from ages 5 to 18, and 632 of them said that music education has a positive effect on academic performance. Assuming these parents to be a random sample, we would like to construct a 95% confidence interval for the proportion of parents who believe that music education has a positive effect on academic performance. So we have a sample. Here's our sample size. We sampled N equal to 800 parents. And we got an X of 632. So this is our P hat. And remember, we know all about sampling variability. We don't know which P hat we have. Do we have one that's really close to the true proportion or really, really far away? I mean, that's a pretty decent sample size, 800. So there shouldn't be that much variability, but there's still going to be some. So we want to check the assumptions and conditions first. Oops, wrong way. There we go. So we have a random sample because we were allowed to assume that the parents were a random sample. We have a sample size of 800, which is definitely less than 10% of the population of all parents with school-aged children. So then it would be safe to assume that the individuals within the sample are independent. And in this case, we have 632 successes. Which means we have 168 failures. All I did to get this 168 was I took 800 minus 632, right? Because we're told that 632 parents said it was positive, which means 168 said that it was not positive. So let's actually do this calculation by hand. So we have a P hat of 632 over 800. When you do this calculation, you get a 0.79. So 79% is our sample proportion. We want a 95% confidence interval. So the C level is 0.95. So we want to find the Z star that's associated with that C level. We can use the inverse norm command, which I showed you on the previous slide with 0.95, or just use the table. After a while, you calculate it so many times or look at the table so many times that you know that this is a z star of 1.96. And so that means that our confidence interval, so our 95% confidence interval, and I abbreviate it like this, is going to be the p hat plus or minus the z star times the number or times the standard error, which is going to be p hat q hat over n. So our p hat is 0.79, 79%, plus or minus this 1.96 times 0.79 times 0.21 over the sample size, which is 800. And this will give us 0.79 plus or minus 1.96. If you put all this in your calculator, you get 0.0144. So the standard error is 0.0144, or like 1.44%. When we multiply that by the 1.96, we get a 0.79 plus or minus 0.02. So this piece right here, this is our margin of error, our ME, margin of error. So now if we physically take 0.79 and subtract 0.0282, we'll get the lower bound of our interval, which would be 0.7618. And then if we take 0.79 and add the margin of error, we'll get 0.8182. So what do we know about this? We know that we don't know, sorry. We're about 95% sure that the population proportion is somewhere in this interval. We don't know for sure where, and we're not 100% sure it's in there. We're about 95% sure that it's in there. We're going to interpret this interval in a future slide. I want to first show you how to use your calculator to find this confidence interval. So same problem, and we have the same information here. We have the x is the 632 and n is the 800, giving us a p hat of 0.79. So we are going to conduct a one proportion z interval. It's one because it's about a single survey question, proportion because we're talking about proportions, and a z interval because we are using a normal distribution. In the next chapter, we're going to use a slightly different distribution. So you are going to go to Stat, and then Calc, and then you're going to arrow over to Tests. This is wrong. You don't do Calc. Let me erase that. We're going to do Stat Tests. And we're going to choose the one prop z interval. And that's the way it's abbreviated. So let me start this here. So you're going to go to the Stat button, arrow over to Tests, and the one prop z interval is all the way down. You have to go down, I think it's A. Yeah, it's right there. So it's going to ask you for the x, which is the 632, the n, which is the 800, and the c level, which is 0.95. So when I'm writing out the work for this, I always write those down. You want to tell me what you put in your calculator. So we have this, and a c level of 0.95. And then you're going to choose Calculate. And it gives you the answer. And so we get an interval, again, of 0.76178 and 0.81822. So as you can see, this is really fast to do in your calculator. And again, it wasn't that much work to do it by hand, but they are going to get more complicated. And the point is to interpret these. So let's look at the interpretation on the next slide. So before I talk about interpreting everything, I want to discuss the margin of error in a little bit more detail. Because a lot of times we're asked to find the margin of error, and your textbook is always going to use the formula. But if you know the interval, then you know the margin of error. Because, oh, what happened? There we go. Sorry, flipped a slide. So if we're looking at this interval, we know that 0.79, the p hat, is right in the center of our interval. And we know that at the very end is 0.81822, and at the lower bound is 0.76178. The distance from the edge of the interval to p hat is the margin of error. And it's the same on both sides. Right? We took the p hat and we added the margin of error to get the upper limit, and p hat minus the margin of error to get the lower limit. So if you know the interval, there's lots of different ways that you can actually calculate the margin of error. You could take the upper limit minus the sample proportion. You could take the sample proportion minus the lower limit. But most people, what they do to calculate the margin of error is they use the upper limit, which is 0.81822. They subtract the lower limit, so they find the distance between them, and then divide it by 2, since we know it's exactly half of that distance. And in this case, again, we calculated this by hand, but we get 0.02822. Or a lot of times we talk about margin of error in terms of percents, so we would say that this is approximately 2.8% margin of error. Okay, now let's get into interpretation. So when we're looking at this interval, what can we then say about the true proportion of parents that believe that music education has a positive effect on academic performance? And this is how we word it. We say, we are 95% confident that the proportion of parents who believe that music education has a positive effect is somewhere between 76% and 81.8%. We don't know where it is in this interval. We're not even 100% sure, right? 5% of the time we're completely wrong. But 95% sure that P is somewhere in here. We just don't know where. It could be 76.2, could be 81.8, it could be anywhere in here, and we don't really know. We just think that it's in here, and we're pretty confident about it. So that's kind of what we're saying here, is that it's probably true that the true proportion is between here. But remember that every time that you take a sample, you're going to get a slightly different p hat. So maybe next time you take a sample, you get a p hat that's 81%. And then the next time you get a p hat that's 74%. And every time you get a different sample proportion, you get a different confidence interval. Well, what we're saying is that 95% of these confidence intervals are going to capture the population proportion, but 5% of them are not. 5% are going to be duds, and it's not going to actually capture the population proportion. So what does that mean when we talk about claims? So say we have one music teacher claims that 80% of parents believe that music education has a positive effect. So notice they're giving one value. 80% of people believe this. Does our confidence interval contradict this claim? No, it doesn't contradict the claim. 80% is in the confidence interval, so 80% could be the population proportion. But we don't know that for sure. Again, the population proportion could be 76.3% or 81% or 78%, right? It can be any of those values. So while our interval doesn't contradict the claim, we don't know that this claim is actually true either. So we just know that the claim is, we would say, plausible. Now suppose that we have another music teacher that claims that more than 3/4 of parents believe that music education has a positive effect. So more than 75%. Does the confidence interval support that claim? So notice I'm asking a different question. The second time around, I'm asking if it supports the claim. And we're going to say yes, our interval supports this claim because the entire interval is above that 75%. If that wasn't the case, if some portion of our interval was below the 75%, it wouldn't support this claim. But because the entire interval is above 75%, then saying that the true proportion is above 75% is supported by our interval. So I'm going to just make one more comment on the margin of error. So I want you to notice what happens with the margin of error when we become more or less confident. So if we have a 90% confidence interval, so I just threw this in my calculator the same way I did the 95% confidence interval, and I got a margin of error of 2.4%. On the previous slide, remember that we got 2.8% for a 95% confidence interval, and a margin of error, if we upped this to 98%, would be 3.4%. So notice that the more confident we get, the bigger the error. So I always think of it as like a target. If you want to be really confident that you're going to hit the target, you want a really big target. If you have a smaller target, you're going to be less confident that you're going to hit it. So a large confidence interval is going to be, or have a high confidence level is going to have a large confidence interval, a large target, so that you can be confident you're going to hit it. Okay, I'm going to do one or two more videos after this.